So I need to write it, and then I'm going to do an example. We're actually going to do 2 examples, and we can come back. The notation's a little tough, okay? But I need to talk to you about error that we might get associated with different polynomials. So for example, we know, like, actually, I'm going to do this. I'm going to say, we know that e to the x is approximately equal to this 3rd degree polynomial. Okay? And this is actually called the 3rd degree Taylor polynomial. You could call it a Lagrange polynomial, but I think the book uses this notation, T for Taylor polynomial 3rd degree. And it is equal to the polynomial. Okay? E to the x is approximately equal to the polynomial. And the question might be, like, how good is the approximation? Well, you can tell me, I think, when was that approximation really good?
For all values of x.
When was this approximation really good?
When we had a lot of terms.
When we have a lot of terms, it's very good. We don't have a lot of terms. We only have 4 terms. It's 3rd degree. So when is this approximation good for approximating e to the x?
With a lot of terms.
It doesn't have a lot of terms.
Oh.
So these, say again?
What interval?
All right, so where are we? What is this interval that we're close to? I mean, obviously, I agree. For e to the x, if I add more terms, it's going to be a better and better approximation. The Taylor polynomial is going to be a better and better approximation for e to the x for all x. But for now, if I only use 3 or 4 terms, where am I going to be good for?
Just very small.
Where? Say it loud and proud. Louder? That's like...
0 to 1.
All right, so somewhere, I'm going to say somewhere around 0. And I actually think it could be like -1 to 1. It could be -0.5 to half. But where is this centered? It's centered at 0. So this is going to do a great job for 0, because as a matter of fact, e to the 0,
1.
1. Look at the Taylor approximation. It's 1 plus 0 plus 0 plus 0. So for those of you who are pictorially inclined, right, here's an example of e to the x. E to the x is the pinkish function. And here's, t1 is the black line. That's the 1st degree polynomial. Does it make sense that it's linear? Yeah, we did that, back in September or October. T2 shares not only the slope, but also the slope and concavity. So notice it's this green one. It has the same concavity. And T3 near 0 shares the concavity, the slope, and the jerk. I mean, if you were thinking about a physical interpretation of the 3rd derivative. And we don't have the 0th degree, but I think the 0th degree would look something like...
I thought jerk was the 4th derivative.
Oh, the acceleration? Is that better? Well, yeah. Yeah, whatever acceleration of a curve means. That's crazy, right? I don't know what the physical interpretation of the curve is. And this would be the 0th Taylor series, right? That is, it does a great job approximating right there. But that's it. All right, so back here, how good is it, right? Well, there's something called a Taylor remainder. It's also sometimes called a Lagrange error. And here's what it says, no proof. It says the error is less than or equal to, now I'm going to write it and it's going to look, the notation is going to look overwhelming, but then we're going to see that it's not all that bad, and we'll do an example. The error is less than or equal to, whoops, let me try again, sorry. Okay, so it looks crazy. It's z.
It has to do with the next term.
Right. So great insight. So Julian sort of takes a little bit of the angst out of it by saying, hey, that's just the next term, right? Now, this is a little bit of a nutty notation, right? The n plus 1th derivative at z max, like what does that mean? But if we ignore the z max notation, this says, hey, it's just, if this is the 3rd degree, the error is going to be less than the 4th degree term because it's the 4th derivative at some value over 4 factorial times x minus a to the 4th. It's just going to be less than the next term, which actually resonates because that's what the alternating series error is. It's going to be, the error is going to be less than the next term. Now, we don't know exactly what the error is going to
I'm a
be.
little bit confused with Z maxes.
I know. I think I said that 2 or 3 times. I know you're going to be confused. So we're going to do an example. I'm going to explain much better what that is. So it doesn't tell us what the error is exactly, because if we knew what the error is exactly, then we'd be able to approximate exactly, because we'd just take this and add the error, and it would be the exact value. All this does is put an upper bound on the error. Okay. So can we get back to David's question? Like, all right, I see it, but what does this z max thing mean? Can we talk about that? All right. I'm going to do it with an example. Okay, so I'm going to take e to the x and say, hey, how good does the 3rd degree Taylor polynomial approximate e to the x? So the question becomes, what is the maximum error for the 3rd degree Taylor polynomial approximation of, let's we have to approximate something. So can we approximate e to the 1st?
Can we, or
Oh, I'm saying, like, are you all right with approximating e to the 1st?
yeah.
So we're going to use this to approximate e to the 1st. So this says, hey, e to the 1st is approximately equal to 1 plus 1 plus a half plus a third. And we know e is not equal to that, but we know it's close, right? How close? Okay, I can tell you that. So the error is going to be less than or equal to. So if I'm talking about a 3rd degree Taylor polynomial, what derivative am I talking about? Talking about the 4th derivative of z max. What does that mean? All right, coming back to that. Over 4 factorial. And now I need to figure out what x is and what a is. Well, a is my center. And great. And x is the value we are approximating. I should say the x value we are approximating. So in this case it's 1. So I'm going to write 1 minus 0 raised to the 4th. I'm going to pause there, and I still know we have this like z max thing hanging out there. But before we talk about that, are people okay with just that setup?
So if it was a 5th degree polynomial, it would be 1 minus 0 to the 6th.
Yes. And can we talk about that just a little bit? So if I'm evaluating at 1, can you see that if it's to the 4th or 5th or 6th, that's not going to change? But can you imagine if we're evaluating at 2? Yeah, right. It's now 2 to the 4th, or 2 to the 5th, or 2 to the 6th. So you can see that when we get further away from the center, it's worse. But just to make you feel a little better, if we were doing like if we were trying to find the error using the 6th derivative, it would be 2 minus 0 to the 6th, but we'd be dividing by 6 factorial, right? So this number definitely gets big, but the denominator also gets big. So there's a little bit of an offset there. But the conceptual understanding there is if you want to approximate further away from 0, you better use more terms. Okay. All right, ready to tackle this guy? What does it mean? All right, so what it means is on the interval that you're approximating, and in this case we're approximating on this interval from 0 to 1, right? So when we're approximating 1, we're actually approximating, we're looking at the Taylor series from 0 up to and including 1. So I'm going to say, hey, we're looking at from 0 to 1. This means what's the maximum of the fourth derivative on that interval? Okay, so I know my function is e to the x. First derivative, e to the x. Second derivative, third derivative, fourth derivative. So,
and you know where we're evaluating from 0 to 1 because we're only asking up to the first.
say that again.
So you know that like our interval is from 0 to 1 because we're approximating either.
Right. And I will say this. Well, actually, I'm going to say it in a second. So this, whoops, sorry. This is asking the question, what's the maximum value that e to the x takes on the interval 0 to 1?
E.
Do you agree? It takes on the biggest value when, in this case, x is 1. And actually, it makes sense. It takes on the largest value when they're furthest away from the center. Very, very often, the n plus 1th derivative, the maximum value is going to occur farthest away from the center. Very often. Not always, but very often. All right, go ahead.
Where does that interval 0 to 1 come from?
Well, where's this centered?
Centered at 0.
0. And where are we approximating?
For e to the 1.
1. Okay, so the x values we're talking about are x from 0 up to and including x equals 1 because that's where we're approximating. That's the value we're plugging in for e to the what? E to the 1. Now you could imagine maybe someone saying, hey, look at the interval from -1 to 1. Right? Well, if you look at -1 to 1, the question becomes, where does e to the x take on its maximum value from -1 to 1? And I don't need to take the fifth derivative to find maximum values. I know what e to the x does. E to the x is increasing. So I know it's going to take on its maximum value the farthest to the right I go, at 1. Now,
So the reason nice, we're just looking at E in this case.
right, so the maximum value that this takes on is e. Now I'm going to, oh yeah, well, I'm going to drop the opposite value because I know e is positive. That's
So
okay.
it's evaluating the fourth derivative at 1, basically.
No.
So Zmax is equal to E or Zmax is equal to 1? Sorry.
Say that one more time.
Is Zmax equal to E to the 1 or is it equal to 1?
So maybe it's better if I write this. Right, so what I'm trying to say is the
Oh.
maximum value that the fourth derivative takes on some interval, and the z represents it. The derivative has to take on a maximum value somewhere. What is that z value, and what y value does it produce? I think the book calls this whole numerator m. I think it just simplifies it and says it's m because it's trying to encourage you to think about it as a maximum value of a derivative on an interval. I've seen different notations in different books. This is the way I learned. I don't know that it's the best notation, and if you find it a little confusing, I apologize. It goes better with a verbal explanation than just seeing the notation. Okay, so, hey, the theory behind this is I don't really know what E is, right? If I knew what E was, I wouldn't need the approximation. But I know a number that's close to E that's a little bit bigger than it. Say again? 3. So,
Wait. Is that just sort of arbitrary?
no, it's not arbitrary.
I mean, can we also put in like 2.8? Because
You could, but here's what I'm trying to do. I'm trying to keep it simple, and I'm going to say, hey, if we know the error is less than or equal to e to the over 4 factorial, I also know that the error must be less than 3 over 4 factorial times 1 to the 4th. And you could do 2.8, but I'm trying to keep it simple. If you did 2.8, your error bound would be smaller and would be better.
right.
Okay. 3 over 4 factorial is what, 1/8? I think so. Don't the 3's go and you're left with 1 over 4 times 2? So, in other words, what I can say is, if I use the 3rd degree polynomial, Taylor polynomial, I can be accurate in approximating e.
Shouldn't it just be less than instead of less than or equal to? Because if it could be, how could it be equal to
e
that?
is, so we don't know if it's actually equal to 3. We just know that it's.
Yeah.
really less.
So, maybe your maximum error is actually equal to the biggest it could be. Like maybe it is. But I do know this. I know that at most my error is going to be 0.125. And what I'd like to do is I'd like to go to the calculator, I'd like to do it, then I'd like to come back to this and do some questions. So if I go, whoops, I think my finger is, I highlighted. Let's change that. Whoops. I don't want to insert text. So if we say, all right, 1 plus 1 plus a half plus a third, we get 2.83 repeating, so what's that, like 5/6? We know, we have a calculator, right? So we know what E is approximately as good as your calculator would. So I'm actually going to take E and I'm going to subtract my approximation. And lo and behold, is that error within 1/8? Is that within 1.125? Absolutely. And that's what the error bound tells us. It doesn't tell us what the error is, but it tells us your error at most is going to be 1/8. So I'll come back here. We're going to do another example, but this is a good place to pause and talk and see if we have questions, comments, or concerns.
You should show this to the class next door.
You know, I don't think I said this, but I'm going to tell it to you. So I'm not going to, you're not going to see Lagrange error on a test or an exam, okay? I might put it on a group quiz or something like that. For those of you taking the AP, there'll probably be one question on the exam on Lagrange error, a couple points at most. Not that it's beyond you. Like, I mean, I think you can totally get it. It's just that the notation's a little confusing. You have to think about it a little bit. There's a little bit of like, okay, well, the biggest value it's going to take is E, but why don't we just, say E is close to 3, but not more than 3. So I'm right, we're just saying, hey, this is sort of like a bonus lesson. Great.
Where did you get the 1 minus 0? I know where that comes from, but the 0, that's just A?
So, yep, it's A, which is the center. And we often talk about Lagrange error with sine, cosine, e to the x, the ones that we have memorized. And if you think about all of the ones that we have memorized, they're all centered at 0. Okay? It's not to say you can't calculate the Lagrange error for some series that's centered somewhere else, but that's a lot of work, because if you're not centered at 0, it means you have to find coefficients. So now you're finding first, second, third derivatives to find the coefficients of the new series, and then you're doing Lagrange error on top of that. So that's, I would say, a very involved question, which is why I can, I can tell you, I'm not going to ask you that on a test. Like, I think it's going to be enough just to ask you, like, hey, how do you recenter a series, right? That's a lot of calculation, and you're wondering how.
How do you decide series?
You have to find the coefficients, right? So you have to calculate coefficients. What are coefficients equal to? Well, coefficients are equal to the derivative of the function
Over the
over whatever like n factorial is, and then instead of multiplied by x, it's going to be multiplied by x minus a. Instead of x squared, it's going to be x minus a quantity squared. Okay. Okay. Can we do another one?
No.
I thought it would be helpful. All right, so let's take sine x and let's do let's see, what's that going to be? X minus x cubed over 3 factorial plus x to the 5th over 5 factorial. They do all right?
Yes.
So sine of x is approximately equal to this, which is the 5th degree Taylor polynomial. Did I talk to you about there's a confusion sometimes?
Isn't that the 3rd degree?
So it's not 3rd degree, and I'm glad.
So what's in between are 0.
So it is a 5th degree because the highest order is x to the 5th. There is terminology called order. So, and there's a little bit of like ambiguity. Is this a 3rd order Taylor polynomial because it has 3 terms? Right? So when we talk about order, we're talking about terms. Or would you say that this is actually a 6th order? Because we're missing the first term, try that again. We're missing the 0th term, the 2nd term, and the 4th term. Those are 0 terms. So there's a little bit of ambiguity, like, is this 3rd order because it has 3 non-zero terms, or is it 6th order because there are 6 terms, 3 of them just happen to be 0? And you can avoid the ambiguity by saying, hey, it's 5th degree, right? It is 5th degree because that's the exponent. Okay?
We'll never have the even degree percentage.
Not for sine.
Couldn't you write that and say it's a 6th degree?
Yes, but we're going to...
So,
Yeah, so we're
if
just
you
gonna say
wanted
because
to,
that's all you see, it's a 5th degree.
right? So, is it right? Because essentially, the 6th degree is no different than the
Yes.
5th degree.
When you go to write it out in sigma notation, you treat that as the first term, the 2nd term, and the 3rd term. Like, like here.
I just said it.
Yeah.
So you were looking at that when I just said it. Okay, sorry. So you can go back to the screencast and listen.
All right.
So I'm going to use this to approximate. Let's approximate like pi over 6. So the question is, what's the error? So the maximum error deals with the next term. So you have 2 choices, right? This is why this one's a little harder. You could say that the error is definitely less than or equal to the 6th derivative, the maximum of the 6th derivative over 6 factorial times x minus a to the 6th. But we actually know what the 6th term is going to be. 0,
That just means it's
right?
less than 0.
So
you could say
it doesn't mean it's less than, so I need to be clear. The 6th term, the maximum of the derivative is not going to be 0. Okay? But I know that the 6th term polynomial is going to be 0, so I can essentially say, hey, I can do better than telling you that the error is going to be less than the next 0 term. I can tell you that error is going to be less than the next non-zero term, which is going to be smaller than if I calculated this for the 6th term. So if I did...
Sorry, I'm just
Thanks.
trying to work that through.
So I could say this. I could totally do that. And you can calculate that and you will get an error, okay? It's not going to be 0 because, you know, think about this. The maximum that the sixth derivative takes on from 0 to pi over 6 is not 0.
It's the same as
Oh, okay.
Yeah,
Right.
it should be the fifth.
Right? And 6 factorial is not 0, and pi minus 6 minus a is not 0. So the error would not be 0. But I'm saying I can do better, and I guess this has to deal with what, Greg, you were saying, like, hey, we could actually consider this to be a 6th degree polynomial, so instead of saying 6,
you just do it
Say
as 5.
7.
let's bump it up. Because isn't this error going to be smaller if I do this?
Can we do this? Alright.
It would be the 7th because we could rewrite what we have already as the 6th.
Right.
So we would just use.
So this really does have everything to do with what you said, Greg. This is, you could call this the 5th degree polynomial approximation, but you could also call it the 6th degree. So since we could call it the 6th degree, our error we can make smaller by looking at the 7th. So let's take a look.
Yeah, the 7th has an extra term.
But couldn't we do this for anything? Couldn't we pick an even higher value that's equal to that gets
Well,
us?
yeah, but then
No.
the error would be quite as.
So you can, the problem with, your error is always going to be smaller the more terms you use. With sine, the beauty is you get a term for free. Every term you have, you get the next term for free, because this is the same. And maybe I'll write this. Right? The 5th degree and 6th degree Taylor polynomial are the same polynomial. And that's not true with every polynomial approximation. That's true with sine, right? The 5th is the same as the 6th, the 7th is the same as the 8th. All right, so I have some filling in to do. Where's this centered? 0. So a equals 0. And what x value am I trying to approximate the function for? Pi over 6. So I have pi over 6 minus 0 to the 7th. And now I have to deal with this ugliness, right? I need to figure out what is the maximum value the 7th derivative takes on.
The 7th derivative is negative sine.
All right, so the function is sine x. The first derivative is
Cosine.
cosine x. Second derivative,
Negative sine.
negative sine. Third derivative is going to be what? Negative cosine.
Sine.
All right, now I'm back to fourth derivative, fifth derivative, sixth derivative, seventh derivative, negative cosine. So it's like a cycle.
Yeah.
All right, so the question is this. So the seventh derivative is negative cosine x. What is the maximum of negative cosine of x?
Is not the same derivative.
Say again?
Did I count?
I can't. Did I mess up?
I think it's negative sine. Yeah.
4, 5, 6.
1, 2, 3, fourth.
Oh, I didn't.
Did I mess up?
No.
Fifth, sixth, seventh. I think it's negative cosine, but here, should we let's do it out, because I didn't do it out, and sometimes you can make mistakes when you don't do it out. So
But isn't that like.
so the fourth derivative is back to sine. The fifth derivative is cosine. The sixth derivative is negative sine.
Oh,
I-
no,
so I think
never
it's-
mind.
I think the seventh derivative is negative cosine.
Yeah, I was.
Okay.
I counted them. I counted 0 as the first.
It's okay. And look, that's why I wanted to do it out. I wanted to make sure I knew. So, what is the maximum value that negative cosine, but as actually the absolute value? So, from 0 to so from 0 to pi over 6, doesn't negative cosine look something like this?
Yeah.
So what's the maximum absolute value that it takes on?
The 3 pi over.
Values are y values. So
Y.
values are how high above or below the x-axis. So really the question is,
Absolute value of it.
too.
Yeah, what's
So
the
it's
highest
one.
Zero.
above or below? Cosine goes above or below the x-axis. What's the most? The most it goes one below, right? That's the most because it's the absolute value. So this is 1. And I get pi over 6 to the 7th over 7 factorial. And I want to tell you this. Do you agree that this would be the next term?
Yeah.
Isn't that what the next term would be? And what kind of series is sine x?
Alternating.
It's alternating. And the alternating series would have told us the error at most is going to be your next term. And the alternating series tells us that a lot easier than doing all this work. Right? So if you see a series as alternating, I would encourage you not to use the Lagrange error. That's a lot of work to get the same result you would have gotten if you just said, oh, the next term is x to the 7th over 7 factorial, so if I'm doing pi over 6, it's going to be pi over 6 to the 7th over 7 factorial.
Wait.
Hold
It's
on.
the McLaren series, right?
Yeah.
What's the error of an alternating series? Is that most the next term?
And check this out. I'm going to do pi over 6, and I'm just going to store that. So it's some value. I'm going to store that as alpha a. So this is telling me that the error is less than, whoops, pi over 6 raised to the 7th divided by 7 factorial, which is where's factorial? It's like math, number, complex, probability. The error is going to be like 2 millionths. And that's pretty cool because it tells me if I'd go and plug in pi over 6, that the sine of pi over 6 is approximately equal to pi over 6 minus pi over 6 cubed over 3 factorial plus pi over 6 over 5 factorial within a degree of accuracy of 2 millionths. Let's see if that's true. All right. Alpha a, that's x, minus alpha a to the 3rd divided by 3 factorial plus alpha a to the 5th over, whoops, 5 factorial. Come on. Math. Probably would have been easier just to say, I know 5 factorial is 120. Sine of pi over 6 is 0.5000002. We know what the sine of pi over 6 is, right? 1 over 2. Like, that's pretty amazing accuracy for just 3 terms. Like 3 stinking terms, and we're within 2 millionths. Now, again, pi over 6 is close to the center, right? If you want to go further away from the center, you need more terms. But that's pretty good. Better than our e to the x approximation. All right. Questions, comments, concerns? Go ahead.
So the max of f of 7 on 0 to pi over 6, how did that just turn into pi over 6? Shouldn't that be
It turned
negative
into
cosine
1.
pi over 6?
It's not
Turned
f of
into
7,
1.
it's
How is it?
It's
So-
not f of 7, it's negative 7.
It's just
So when does negative cosine take on, or I should say, when does the absolute value of negative cosine take on a maximum value? Take on a maximum value. It takes on a maximum value at 0. Right? The cosine of 0 is 1. As a matter of fact, I should say this. For any of these derivatives, sine or cosine, the most it could be is 1, right?
Because that's
I mean, I was just confused 'cause when I graphed it on the calculator, this is negative cosine of x from 0 to pi over 6. It seems that its maximum occurs at pi over 6. But apparently
No. So here.
okay.
right? So just switch that to absolute value, or think, either switch it to absolute value in your calculator, or think what is the furthest above or below. Okay? And that's why those absolute value signs are important.
Alright.
Is that okay? I'll give you another like 8 count. I mean, it's like a little like involved, right? I don't think it's like necessarily super hard, but it's confusing and a little involved. You got to keep some steps straight. Greg?
It's not really related. Well,
That's okay.
Is the graded assignment tonight all on this?
Yes. So not all on this. I think it's your last one.
Wait, really? That's, oh my god. I can't believe it.
Did you ever
Cry
think?
tears of happiness.
Did you ever think like back in September when you were on like graded exercise 3, you'd ever make it to 60 something? So I believe there's a chart of first, second, third, fourth degree derivatives, and you need to use those derivatives to write a Taylor series, and then to come up with the error. And if you understand that the error is based on the next term, you're going to see why that fourth derivative column is going to be important for you.
It's not conveniently alternating, is it?
I don't think tonight's is. I think tonight you actually have to think in terms of Lagrange error being.
Of course.
And there are two from the book. So the first two I think say just come up with the Taylor polynomials, and then the next two say, hey, if you're going to use these Taylor polynomials, what is your maximum error? And I don't think they're alternating. I think they are non-alternating series that you have to use Lagrange error for. But if you go back just originally to circle all the way back to what Julian said at the beginning, all it really is, it's the next term in the Taylor polynomial, but the twist is you have to consider the biggest value that the numerator could take on. And that's the twist. That's what makes it a little different. But you can do that. Right? Anything else?